All right, today we're going to be looking at a review of polynomials and rational functions. They're going to come up all the time in this class, so we need to make sure that we're comfortable with them, and we know how to recognize them, and we know the basic details of what we're going to have to deal with when we interact with one of these functions. So we'll start off with polynomial functions, which are very nicely behaved. And your most basic polynomial function is, in fact, just a line. Right? A line, if you look at the definition for a polynomial, a line meets the definition for a polynomial. Now, usually we treat it separately than other polynomials because there's a couple of special things about lines. One, they're significantly simpler than our other tools that we use for polynomials. So you're kind of overdoing it if you bring in a lot of your polynomial tools to deal with lines. All right, it's kind of like using a sledgehammer to put a thumbtack in the wall. It's just way too powerful of tools. We have much easier tools to deal with lines because they are so much simpler, right? If you think about a typical line, it's much simpler to deal with than even a second degree polynomial, a quadratic. Okay, and the thing is, lines come up frequently. They come up all over the place in calculus, right? A lot of calculus, our tools in calculus wouldn't really work without lines. So tangent lines, all the kind of stuff we're going to be studying, we need to be comfortable with lines. But keep in mind, lines are just the smallest degree polynomial that is, meaningful. So all the tools that you have for polynomials, you can apply to lines, right? That's perfectly acceptable thing to do. So from there, we start building into more complicated polynomials. So by increasing the degree of a polynomial, you increase the complexity that polynomial can have. So here we have a first degree polynomial, which is just a straight line. We change that to a second degree polynomial, and now all of a sudden we have a more complicated structure that we're looking at. And this thing, as we've seen with our transformations, we could make this parabola skinny, we could stretch it out, make it wide, we could flip it upside down, we can move it around on the graph. So all sorts of versions we can do with this line, whereas the straight line, you pretty much get that one shape. Sure, you can change the slope with it, but with quadratics, we can actually get different shapes. They're all parabolas, but different shaped parabolas. And then as we go up from there, we can get even more complexity. Here we have some turning points, and we have various different third degree polynomials that can take on different shapes and have different characteristics in them, okay? Now, one thing we want to remember about polynomials, they are smooth, continuous curves. That's going to make them very easy to deal with. Continuity makes things a lot nicer to deal with, and the smoothness is going to make things easier to deal with. So we really like polynomials. In general, when you have to deal with a polynomial in this class, you're usually going to be glad about it because they behave better than a lot of other types of polynomials, okay? The next thing we want to look at is rational functions. So the next thing we want to deal with is rational functions, right? Remember, a rational function is really just a polynomial over a polynomial. So it's a fraction with a polynomial in the numerator and a polynomial in the denominator. So there are various things we have to do in order to go through and figure out what are these all about. So if we look here at this fraction, remember, when is a fraction equal to 0? A fraction is equal to 0 when the numerator is equal to 0. Well, in this case, we can see that the numerator of this fraction will be 0 when x is equal to 3. So that would mean that our x-intercept should be at the point 3, 0, and sure enough, that's it right there. And we can see there won't be any other x-intercepts because we don't have any other places where our numerator can be equal to 0. Another question we want to ask is, what is the domain of this function? And we'd also like to know if there are any vertical asymptotes. Now, most of the time, these end up really being the same thing. There are times where you can have one without the other, right? So you can have an undefined point that is not a vertical asymptote, right? But most of the time, when these rational functions that we look at, the undefined points are going to be where the vertical asymptotes exist. So we can get all of that information at once. And remember, where a fraction is undefined is when the denominator is equal to 0. So if we look at our function here, x plus 5, we think about, well, when would x plus 5 be equal to 0? That's when x equals negative 5. And sure enough, if we look at x equals negative 5, there's our vertical asymptote right there. And if we zoom out, we can definitely see that vertical asymptote existing. Now, this occurs for more complicated functions as well. All right, and here we have a more complicated looking function, but you know what? We apply the same tools in the same way. It's just that here we're going to have to factor things in order to solve where is the numerator equal to 0 and where is the denominator equal to 0. So in the previous problem, the polynomials in the numerator and denominator were so simple, we could just eyeball it and go, yeah, I can see where this is going to be 0. Here it's a little trickier. I didn't come up with a very complicated problem, but you can see what you have to do is set these equations, set the numerator equal to 0, solve that, you'll get your x-intercepts. Set the denominator equal to 0, solve that, you'll get your asymptotes, your vertical asymptotes at least, and then we'll have a whole bunch of information about this function. So let's see, if we set the numerator equal to 0, that's a difference of squares. So, set this equal to 0, you get x plus 2 times x minus 2. Go through, solve that, you're going to get 2 and negative 2 for your zeros in the numerator, basically where the numerator is equal to 0. And sure enough, if we look at 2, 0, and we look at negative 2, 0. And there you go. We've got our x-intercepts right there. So we found those relatively easily without having to do too much. Set the numerator equal to 0, solve that using factoring, or if it's not factorable, use the quadratic formula. Whatever you have to do to get those solutions, that's going to give you those intercepts, the x-intercepts. Okay, so then what about our vertical asymptotes? Well, now we set the denominator equal to 0, and if you factor out an x, you're going to get x plus 3 times x. That means that we have a vertical asymptote at x equals 0. Sure enough, we can see that one showing up right there, and we get one at x equals negative 3. Sure enough, we get that one right there. So it's really nice that we can easily check our work by looking at the graph. That's why it's really handy to have a graphing calculator in this class. And it's also really handy to have Desmos, because you go through, you do the algebra, you get some answers, take a look at the graph on Desmos, and you can verify that your answers are correct visually. We're going to do a ton of that in this class. You do some work algebraically, you use the graph to verify that your work is correct. We're also going to look at graphs, try to figure out some information, and then verify it with the algebra. So you really have to be able to go back and forth between the algebra and the graphs in order to make sense of everything. So that's how you get your vertical asymptotes, that's how you get your x-intercepts, and that's where you find your undefined points. One really important topic that's going to play a huge role in this class is end behavior. So in pre-calculus or college algebra, whatever you took before this, we have this idea of end behavior that we learn about. Well, in calculus, all that end behavior is going to be used on a regular basis. The difference is that in calculus, we call it limits. We call it limits at infinity, limits at negative infinity. We're going to learn a whole bunch of different types of limits, and one of them is largely concerned with what we, in a previous semester, is called end behavior, but in calculus, we call it limits at infinity. So it's like if you're comfortable with end behavior, that's great, because you already have learned like 90% of what you need for that particular topic. You just have to put it into the language of calculus. If you're still kind of struggling with end behavior, you definitely want to go back and brush up on that material, because it's gonna play a major role here. So remember, end behavior is what happens at the ends of the graph. So in the middle of your graph, you have all sorts of different behavior going on here, right? We can see we've got, as we just worked through a minute ago, you've got x-intercepts, you've got vertical asymptotes, you've got places where the function is increasing. In fact, it looks like it's increasing everywhere except for where it's undefined, right? We've got all sorts of behavior in here, but what tends to happen on the ends of graphs is the behavior mellows out, right? At some point, they just take on some behavior and they continue that. They don't start having more curves or anything like that. That's what end behavior is a description of what's happening on the ends. What's happening at the extreme values for x. So imagine starting here at 0 and going down the x-axis in the positive direction, and you pass 10, you pass 100, 1,000, a billion, a trillion. You just keep going on towards infinity forever. What is the behavior of this graph? And then we have the alternative on the other side where we're going towards negative infinity. What's the behavior on that side? So sometimes a rational function will have the same behavior on both sides. Sometimes it will have different behavior. So we want to remember how this works, so that way next chapter we're all ready to put that into the language of calculus. So there's three cases The book gives you a blue box here to kind of help you remember how end behavior works. And we're basically going to see the same box again next chapter, but we're going to be putting it in a new language. So it's the same mathematics. There's very little like new mathematics to learn. It's just a new structure in which we're going to be interacting with the end behavior. We're going to refer to it a little bit differently. So the three cases they boil down to taking a look at the degree of the numerator and the degree of the denominator and trying to make sense of what that means for the ends of the graph. So if you look at, and this is a case where I see students trying to memorize these rules, and sometimes that works okay, but I see students get really confused when they've memorized the rules but don't really understand them, and then the test comes around and then they're really struggling with it. The concepts here, if you can wrap your brain around it, they're not too bad. If you can understand what's happening here, then all of a sudden what's going to happen is it's just going to make sense. You don't have to try to memorize what these rules are doing and then getting it mixed up. If you understand the underlying mathematics, you just think about it for a second and go, oh yeah, that's what's happening here. So if we look at the degrees of the numerator and the degrees of the denominator, this is one of the three cases. That's where the degree of the numerator is equal to the degree of the denominator. And what happens in that case, it ends up being the ratio of the lead term on front over the lead term on the bottom. So in this case, we have a 1 coefficient in front of our x squared, and we have a 1 coefficient in front of the x squared on the bottom. So that ratio would be 1 over 1, which is 1. And sure enough, if you look at our horizontal asymptote, y equals 1. Right? That's not by accident. That's because it's the ratio of those leading coefficients. Because if you think about it, our numerator is blowing up at the speed of a quadratic. Our denominator is blowing up at the speed of a quadratic. They're essentially blowing up at the same speed. So any kind of growth we get in the numerator, we're getting that same growth in the denominator. So when you look at the ratio of those things, which is what a rational function is, we end up with the value 1. Okay, so what if we change this? Now that we've changed the coefficients of those lead terms, we have a different ratio now, and we do not have the same horizontal asymptote. We can see pretty quickly this is not the correct horizontal asymptote because neither one of these curves is approaching it. So what do? We look at that ratio of 5 over 2, which is 2.5, right? So if we make this line now become 5/2, all of a sudden now we've got our horizontal asymptote and we totally understand the end behavior of this function. Okay, so there's a couple other cases then. So what if we change this to where the degree of the denominator is bigger than the degree of the numerator? So let me make this a third degree polynomial. All of a sudden things are very different. Now we can see in the middle of this graph that we're actually crossing the horizontal asymptote. You can cross a horizontal asymptote in the middle of the graph. That's fine. What doesn't happen is crossing a horizontal asymptote on the ends. What happens with the horizontal asymptote, your function gets closer and closer and closer to that asymptote, but it never actually touches it on the ends. It can touch it in the middle. In fact, this one's going to touch it a couple times. So if we think about what fractions do, as we're putting in extreme values for x, so remember when we talk about end behavior, we're talking about going down that number line and putting in extremely large values for x. Don't even think of numbers like trillion. Think of numbers that would have 1 million digits in them. How big of a number is that it has 1 million digits? That's way, way down the x-axis, right? Well, when we plug in really, really large numbers, we're going to end up squaring that number in the numerator, but we're going to cube it in the denominator. So when you cube a really, really large number, it's going to be vastly larger than when you square that big number. So essentially what's happening is the numerator is growing at the pace of a square, and the denominator is growing at the pace of a cube. So the denominator is outpacing the numerator. So think about what happens when you have a fraction with a big denominator and a small numerator. That fraction is going to shrink down towards 0. And in fact, we can see that in this case, our horizontal asymptote is y equals 0. Okay, we can see it going down and approaching that. Again, we can cross it in the middle of the graph, in the sort of finite area we're concerned about. But once our behavior levels off and we start worrying about going to infinity, we can see the curves just track that horizontal asymptote and they get closer and closer to it, which is very convenient for us to now understand that behavior. Now, here's a case where we see, this is our last case, the degree of the numerator is greater than the degree of the denominator. So in this case, we have no horizontal asymptote. Okay, so the end behavior is just, well, over here on this side, our values are shooting up towards infinity, and over here, they're shooting down towards negative infinity. Now, we have a special case here when the degree of the numerator is exactly one more than the degree of the denominator. We get a special case of what's called a slant asymptote or an oblique asymptote, okay? Which means basically this side's going to infinity following a line. This side's going towards negative infinity and following a line. In fact, we can kind of see if we put one in there, it looks like it's in angles. We can kind of see here, we start to see, oh yeah, it does look like it's following that line right there, right? And that's because it is. So sometimes we care about how they're going to infinity. Most of the time we don't care. If one end's going to infinity and the other end's maybe, like in this case, going to negative infinity, that's usually what we're going to care about. On rare occasions, you will care about how they're going to infinity, but usually not.